Hello, everyone. I hope I'm audible.
Yes,
Perfect. All right. So I guess the participants might take some more time to join. So what we will do is we'll do a quick recap of what we covered yesterday, and we'll continue with today's session. So if I as of yesterday, we started with a analyze phase when we discussed briefly about the seven quality control tools. Uh, these are something which we have already kind of worked upon, like histogram. We talked about check sheet, flow chart, cause and effect diagram. We're coming to Pareto chart. Now, Pareto chart is what we worked on, which was the 80-20 rule to prioritize and find out most critical problem based on the frequency. If you have high repetition of a particular problem, you will be able to figure out where is the maximum problem coming from using Pareto chart. Now, scatter plot and control chart, we're still parked, and the scatter plot will be able to cover up today itself when we going through the statistical test. It is going to be part of one of the test. Control charts being parked up for the control phase. Now, just to make sure we all have a very clear understanding about what is a null hypothesis and an alternative hypothesis, keep this in mind. Thumb rule: null will always talk about two variables. We're comparing two people, you're comparing two shifts, you're comparing any two groups. Null will say that there is no difference. Even if you're comparing more than two groups, as per null, they all are same. There is no difference in the groups that you're comparing. Null always talks about these kind of things. So the productivity of machine manager 1 is same as 2, as same as 3, as same as 4. So technically there's no difference. Alternate will always come with a contradiction. Alternate will always try to prove a point. I might be trying to prove it's greater than the value, whatever we're claiming in null. Like we talked about, chocolate is equal to 500 grams. BMW will give is giving 75 kilometers per liter average, sort of thing. Whatever we claimed in uh, as null, we try to prove that is wrong. So we can prove it by either less than, greater than, or not equal to. The only thing we need to prove is an alternate statement because null is already proven existing truth. So we never prove null. Null is already proven. We're only trying to prove an alternate because we have a problem with what's stated in null. We don't think it's right. So we have a claim, we have a challenge, and we would like to submit some evidence. Now, where is that evidence going to come from? The p-value. We talked about the p-value. Now, based on the p-value, we will decide whether null statement is right or alternate statement is right. Now, thumb rule, this is what will apply in every test. Everything that we will do in statistics will be based on these conditions. If a p-value is less than 0.05, you will reject the null and you will accept the alternate. So p-value less than 0.05 is when you reject the null. If it is equal or more, you'll continue to go with the null statement. Now, one thing we would like to before we move ahead, just want to make sure that we should understand. We understand what is a p-value. We're talking about the risk of alternate. Null risk is already known. This is fixed, 5%. Uh, where is this risk? Like we're trying to only understand how much is the risk in your alternate. Now, why we comparing only with 5% is what we got to know because we have got a 5% alpha risk. Now, there would be organizations which are like critical organizations where they're working with, say, 99% confidence level. If the organization is working with 99% confidence level, that leaves them with 1% risk. That is 0.01 of alpha risk. Then the similar comparison will happen in those industries as per this criteria will be less than 0.01. That's the left out risk. We want to see if which confidence level we are working with. So as we already discussed, uh, p-value is all generally default stated as with comparison of 5% because we always do all statistical testing at 95% confidence level. Now, only if your industry requires a different kind of confidence level, you're dealing with an industry which is like a very critical industry where there's a life and death situation is at stake. Those industries work with 99% confidence level. You can make those changes. That would not be a problem. You can, whenever you do statistical testing, you have an option to change and your confidence level. So you can change the confidence level and your decision will be done on this criteria. But for now, we'll just stick around to this because this is what will be used as standard thumb rule. Now, having said that, when we talk about this p-value, that's the evidence which we are looking for, which will help us understand if null is right or alternate is right, looking at the p-value. Just the basic stuff which we got to keep in mind, like there are types of error, mistakes that we might do. There are two types of error which we can make when we're dealing with these error, these null and alternate, so as to say. Now, these errors are possible. There's something called type 1 error. These are mistakes, and you may call them as alpha error, or you may say innocent punished situation. So the situation is like innocent has been punished. In a court, if somebody has been, like, somebody is really innocent and that person is proved as a criminal because somebody gave wrong evidences in the court, people gave wrong witnesses, like sort of thing, whatever. That's a mistake made by the court. What kind of mistake? It's a type 1 mistake, error done by the court, or an alpha error done by the court. That's what is a innocent. So all these meaning means the same. Either you say type 1 error, alpha error, or innocent punish situation. That's a type 1 error. We'll just sort of briefly talk about it. We'll also understand when do we get these errors, when do we make these mistakes, what's the reason of it. This is the opposite of it. Guilty released. A criminal is released because of lack of evidence. We do not have enough evidence to prove that you're a criminal. So people did not come for witness. Well, this guy is released. That's a type 2 error. Is that a mistake? Yes. Should this person be put under behind bars? Yes. But sorry, we do not have evidence. So the person is released. That's a mistake, which is type 2 error. Now, what is, from data perspective, what do we understand by type 1? If you prove null as alternate, you have committed a type 1 error. If there is a p, there's a null statement. That means there's no relation. Everything is same, but you prove that no, there is a relation. There is an impact. It's a root cause. Something which is not a root cause, you prove it as a root cause. You have made a mistake. What kind of mistake? A type 1 mistake. What will happen? You'll continue to work on that root cause because you proved it, that it's a root cause, and you will see no results. Your business problem will not solve. Why? Because in reality, there is no relation. But you made a mistake and you proved it to be impacting factor, root cause. You'll not see any improvement. So that's a type 1 error. This is opposite. If you prove alternate as null, a real root cause because of some mistake you did, and you prove it as null, no relation. You will not work on it, you will leave it, and you would not see any improvement. So both these errors can happen, yes. What is the source of these errors? How do these errors happen? There are two primary sources, and it goes back to your measure phase back again. That's where you baseline your process. One is insufficient data. If you've not done your sample size calculation, you may be a victim of these two errors, either type 1 or type 2 error. You will end up committing such errors. Incorrect sampling method. So both the things that we discussed in the measure phase, they were so critical that it can haunt you throughout the project. So if you've not done your sample size calculation correctly, if you've not collected your samples correctly using good methodologies, unfortunately, you will end up making wrong predictions. And that's how it is. You may end up making these errors. So this is the reason why we spend a lot of time in the measure phase understanding about all the possible nitty-gritties. We, like, traditionally people were not never using calculation formulas, so they were picking any random data like 50 samples, 100 samples. That's not the way. So yes, people were making a lot of such errors historically. Yes, traditionally people have made such errors, huge errors. There were bad sampling methodologies. We did not have the rational subgrouping. We did not have stratified random sampling. We had bad methodologies. there were errors in the sampling process. But now, thanks, we have formulas, we have got good methods. These errors have gone down significantly. But can we ever say that we cannot make these errors? No. You make these issues, again, you will be a victim of these. The moment you have wrong, any you mess up with this process, you will always be prone to this. So it's very, very important. Again, there's nothing much in here, but just got to make sure that these errors are possible. You can come across these errors if you mess up with your measure phase. That's your base. Your data is incorrect, your everything will be incorrect, and there will be mistakes made in this. So null will be proven as alternate, alternate will be proven as null. You will have wrong predictions. So that's what we have to specifically stress a lot in the real world when you're dealing with measure phase. A lot of care has to be taken care of. Is that okay with everyone? Basic stuff, basic, uh, just like the objective is to understand these errors exist, why do they happen, and what is the meaning of a null type 1 error or type 2 error. Because during job interviews, people might ask you this question: what is a type 1 error or what is an alpha error? You should be able to tell when you actually prove a null as an alternate, that's a type 1 error. Simple as that. You should know what is it. What is a beta error? You should know. If a court has penalized somebody who is innocent, what error court has committed, you should know this. So these questions can be framed this way. So you should know all the name, like type 1 alpha error, punished, innocent punished situation, sort of, because recruiters do ask questions this way. So keep that in mind. I hope that's okay. That's a very simple one, but yes, do remember this. These kind of questions can come during the job interviews.
Can you repeat the kind of questions?
Yes,
I
sure.
missed that part.
Okay, if I'm a recruiter, I might ask you what kind of like what is a type 1 error. So I may ask you what is a type 1 error, or what I may ask you like what is an alpha error. So technically, I should be able to say that yes, when I have a null statement and I have proven it as an alternate, that means I've proven it as a root cause. Uh, there I have made a mistake. That is a type 1 error. So when null is proven as alternate, that's a type 1 error. Or the questions could be framed in a different way. People may not, and tech trust recruiters don't give you a type 1 or type 2 generally, but they might even ask you this situation. Well, this is if in a court, like the judge has punished innocent person, what error has been committed by the court? Is it a type 1 or type 2? That's when I should know. Well, it's innocent is punished. That means there was no relation, and we proved there is a relation. So null, no relation, proved as a relation, innocent. So that's a type 1 error. The questions could be asked if there is a criminal, and because of lack of evidence, the court has to release the criminal. What error has been committed by the court? We should know that's a type 2 error. So
All
these
right.
got to keep this in mind. Now, coming straight away, that was the last bit of theory sort of thing. Now we'll be getting into the test part of it. Now, say you've completed your measure phase, you've got your data handy, and once your data is available, you would like to start with your statistical test. So your measure phase data looks like this. Your process is, you've got your data ready. Now, I would like to start my statistical testing. What are the things I should do in a sequential order? What is the process of going ahead? What's step number one? What's step number two? Let's understand it. So hypothesis testing is where we're going to start first. Say your measure phase is over. This is what you will do first. First thing first, we always go for checking normality. We already know what is normality test. How do we check normality? But just to understand what's the sequence, let's put it here. And now we'll be talking about null and alternate with respect to that. So normality testing. Why do we test a normality? Or while we check normality to understand whether I should look at average of the data, whether I should look at median of the data, it helps me find out what's the right metric, mean or median. So how do we test it? Using Anderson Darling normality test. When do this test, we get to understand whether data is normal or data is not normal. What is my default definition with respect to data? Data, default definition, null definition, and default alternate. Data is always normal. These are default statements with respect to data statistics. Data is always normal. Alternate will always have a problem. Data is non-normal. Now, let's understand that's my default statement with respect to any data. Data is always normal, data is non-normal. We have the data. Let's kind of copy paste it here and figure out whether data is normal or non-normal. Let's copy paste everything here just to understand in the language of now, null and alternate. We got this data, we go to stat, we go to basic statistics, and we go to graphical summary. Say I want to go with graphical summary, or I can do a normality test also. Graphical summary, I go with, I want to select this ticket closure time. Ticket closure time is what I selected. Click OK. Now, let it come up. Okay, that's the p-value, norm Anderson Darling normality test. It says p-value is 0.587. 0.587. Let me go back to Excel and let's add it here. So your p-value is 0.587. Would you go with null or would you go with alternate? Null or alternate? P-value is what you got. I'm sorry?
Alternate.
When do you have alternate? When do you have an alternate? What is the condition? What is the criteria?
0.5050.
If it is more than, less than. If your p-value, remember this again, just
More than 5%.
this is what we go with. Please keep this in mind. Again, this is what is the base. Just a couple of lines. You got to remember this always. Please keep this in mind. If it is less than 0.05, then an alternate. Only when it is less than 0.05, it is alternate. If it is less than, otherwise continue with null. That's what you have to remember. If p is low, null must go. Is it less than 0.05? No. So I cannot reject the null. I'll continue with null. So p value when it's less than 0.05, that's when it's alternate. Never. This one is not. So null is what we will continue. This is null. What does this data say? Null means data is normal. So this data that we tested is normal. Basis this. Let's take another example out of this and we should be able to make more sense. Let's say I want to check for customer satisfaction score. Let's check the p-value, customer satisfaction score. Is this data normal or not? It says it's less than 0.005. Let's go back. P-value for the customer satisfaction score is less than 0.005. Is this normal or non-normal? What would you go with?
Non-normal data.
Is it alternate or null?
Alternate.
Like here it's
Absolutely
get
is.
to
Alternate.
reject null.
You reject null. It is you going to reject the null. Is this p-value, is this less than 0.05? Yes, this is less than. It's highly non-normal. Actually, if you look at this value, is it less than 0.05? You have to just do a comparison. Is this less? No. Is this less? Yes. If it's less, then reject the null, accept the alternate. P-value that we got, it is less than 0.05. It is, this one is 0 point less than even 0.005, not 0.05. It's highly non-normal. That's alternate. This confirms that my customer satisfaction data is non-normal. I hope that is clear to everyone. If you have any other questions, still we can take it up. Is it clear how to you refer to null and alternate and take a decision? If it's you need, I can get more data. I can try out more data. Don't hesitate, because if you don't understand how to do this, it's like very simple stuff, but probably if you need more practice, we can do it. I can randomly create some more data and just help, so that we should know this is the base. I can technically, uh, for every test you'll be looking at p-values. Let's quickly have a look at it. Okay, no problem, absolutely fine. Let's have a look at some more examples. Okay, let me create one random data and just copy it there. Let me create one. Say sample. This is the data I want to check about normality. Is this data normal or not? Let's go back here and check it out. What do you see here in normality? And 0.584, 0.584. Let's take it back to the notes. P value for this data is 0.584. 584. Null or alternate?
Null.
Absolutely null.
Null.
Absolutely no doubts about it. Simple question. Is it less? No. Is it less than 0.05? No. So if it's not, then it will continue to be null. If it is more, then it's alternate. Okay, perfect, perfect. So this one is null. So the data is normal. The one which we just created, this data is normal data. Look at this one. Let's create one more sample data. Say let me just create some random data here. Let's see. So I want to create say 100 values. I want to store it under sample 2 with an average of say 20 and a standard deviation of say 7. Okay, let's check for this one. Oops, not this one. Let's check for this whether it's normal or non-normal. Sample 2. Oh, well, it's almost like let's kind of mess around with this, otherwise it will. Oh. Have a look at this for p-value and help me understand, is this data normal or non-normal? Is it's saying it's less than 0.005. Null or alternate?
Alternate.
Alternate.
Absolutely, yes. So this is an alternate. That means that data is non-normal. So look at the p-value and understand, is it less than 0.05? No. Then it's null. If it is less than, yes. Reject the null, accept the alternate. What is null and what is alternate, we know. So with respect to data, we do this testing to understand data is normal or not. So in our case, when we looked at this data, the ticket closure time, that's my business problem. This data is normal. We looked at the p-value for this one. It was normal. So my data is normal. I should be looking at average of the data. That's my first criteria. Now, the second thing which I do once we are done with normality is randomness test. Now that people also call it as test for stability. Is your data stable or not? How do you check it? Using this stability and randomness is same thing. Name of the test is called run chart. Run chart is the test. So if you want, we would understand what is the meaning of randomness and what is the meaning of stability, but let's understand what's the test. It's called run chart. I would like to understand, is my data, this ticket closure time data, is this random or not? Is it stable or not? Let's do the run chart and then understand what is randomness. Quality tools, and the first one is run chart. You click on run chart, select the data. It says subgroup size, single column. So put 1, that's it. Number 1, click OK. Now that's going to be your run chart. Let it come up. Let's kind of double click to get it bigger. God knows what kind of update has happened with my system. Okay. Okay. Now I hope this is clearly visible to everyone. If let me just drag it, I will take a second. Rather weird. Okay. Now let's go back and understand. There are three p-values and they're not a single p-value. There are 4 p-values. Look at this: p-value for clustering, p-value for mixture, p-value for trend, and p-value for oscillation. There are 4 p-values. Now the rule says if any p-value is less than 0.05, same condition. If any p-value is less than 0.05, the data becomes non-random. Any p-value, any of these, clustering p-value, mixture p-value, trend p-value, oscillation p-value. If any p-value is less than 0.05, it will become non-random. Technically, what will say if I have a p-value for mixture which is less than 0.05, that means my data has become non-random because of mixture issue. There's the or we'll have a data we can look at that, but yes, let's kind of put it here. What is the default definition with respect to randomness? Data is always random. Data is non-random. These are Default definitions. Now, how do we know? We would perform a run chart. Now, what do we see in run chart? There are four types of patterns which can be present in a data. Not necessary, they can be. If any data is present, it will, any pattern, sorry, my bad. If any pattern is present, it makes it non-random. A data free from patterns is called random data. How do we know if any pattern is present or not? If p-value for clustering, oscillation, mixture, or trend is less than 0.05, it confirms presence of that pattern. So if any p-value for clustering, oscillation, mixture, trend, any p-value, if it is less than 0.05, that confirms that there is a pattern, that pattern in the data, which is making it non-random. So in our case, we had 4 p-values and all p-values were more than 0.05. This data is random data. Let's look at another example. We'll get clear. It should get clear. Let's pick up customer satisfaction score. We've got customer satisfaction score. We want to check, is this data random or not? Let's hear it from you all. Is this random or non-random? Is it visible when you're kind of looking at the screen? Is it a random data or a non-random data?
Partly random, partly
No, this either data is random or non-random.
non-random.
Why is this non-random?
Because two p-values are less than 0, 0.
Yes. So clustering p-value is less than 0.05. That confirms there is a clustering issue in the data, which is why the data is non-random. And there is a trend issue also in the data, which is also less than 0.05. So you may have issues like patterns, you may not have patterns. If you have pattern, even a single pattern, the data is non-random. Here we have two issues, both trend issue and clustering issue, which confirms that this data has a clustering issue, this data has a trend issue, which is making it non-random. But if there is all p-values are more than 0.05 or equal to 0.05, technically my data is random. So that's how we check for randomness. Now, why do we?
Could you repeat this? I'm so sorry. Could you
Yeah,
repeat this again?
sure. Basically, if any p-value, any of these p-values, if it is less than 0.05, that will make the data non-random and it will confirm the presence of that pattern. Say, in this case, we have a statistical evidence, which confirms that there is a clustering issue in the data. Why? Because it is less than 0.05. Similarly, we also know that there is a statistical evidence which confirms there is a trend issue in the data. Why? Because it's less than 0.05. Hence, my data is non-random and this data isn't based technically non-random. If all p-values are more than 0.05, technically my data is random. Like in the first case, this case is this one. All the p-values were more than 0.05 in the ticket closure. This is greater than, this is greater, this is greater, this is greater. So this data was a random data. The other one is non-random. Is this okay with everyone?
Yeah.
Okay. All right. Now, question is, why do I need to check for randomness? Like, I know what was the purpose of normality. I will get to know, should I look at average? Should I look at median? But what am I going to do with this randomness? What is the purpose? I get to know it's random or non-random. Technically, the reason is one of the statistical tests, which is what we will be using in a short while, Way Anova, can only be tested if data is random. If data is non-random, then instead of ANOVA, we will use Kruskal-Wallis test. Now we'll understand the name of the test and everything. That will make a chart so that we can understand it. But that is the purpose. There are two tests which are there available for testing. When to use that, we'll understand. But yeah, if the data is non-random, then only we can use ANOVA. If it is non-random, then we use Kruskal-Wallis. So there are two different tests, and we have to understand it's random. That's why we would like to check it first. Is the data random or is the data non-random? Based on that, we'll end up selecting the test. So once we have done these two tests, that's when we move on to the hypothesis testing for like the understanding, is it a root cause, not root cause, all the data that we have, everything that we have here. We would like to start the testing part to understand which ones out of these is the real root cause, why we're facing the business problem, whatever business problem we are facing. Let's go back to the testing part and make the data, like the structure for the tests. So hypothesis says this is, we've got a normal y that we're dealing with. You will can have numerical access and you can have categorical access. Let's understand them first. So your data, you have a normal y. Yes, we have a normal y in the data. This is my normal y. And see, if you look at the MINITAB, it automatically understands the data is a number or a data as a text. Look at this. All the data in this case, it's number. You just see C1 here. The moment you have a text, it becomes C2T, text T, alphanumeric, text T, all numbers C6, all numbers C7. So technically, automatically Minitab also identifies data as a number or a text. Categorical is text and number is number. So the test will be based on either you're dealing with a numerical X or you're dealing with a text-based X. If you're dealing with a numerical X, then the statistical test that you do here is called correlation test. And the graphical test that you do is called scatter plot. That's one of the 7 quality tools that we talked about. We'll cover up. That always goes hand in hand with scatter plot. So scatter plot and correlation will always be done together. That's the test for numerical access. So any numerical access that we have in our data, let's check it out first. So this is my y, which is fixed. That's my y. That's my business problem that I'm dealing with. This is a text base. This is text base. This is text. This is text. This is all numbers. This is all numbers. So when you have numerical X, which is like these, I will check CSAT, whether the customer satisfaction score has an impact on ticket closure time. I'll do a correlation. I want to check whether the number of follow-ups has an impact on ticket closure time. I will do a correlation because these are numerical X's. Do I have more numerical X's? No. All these are categorical. So first of all the numerical X's will be tested on correlation. We know what are numerical X's. Now in categorical X's, we have further breakup. We have got 2 groups and we've got 2 plus groups. Now what is this 2 groups and 2 plus groups? Let's understand this, but let's kind of name the test first. If we are dealing with 2 groups, the name of the test is called 2 sample T test. The graphical plot will be box plot. We already know box plots. We have already done this. This is where it gets predominantly used. And here we have the test called Way Anova that we were talking about. Way Anova we have to do. And the test is box plot again, graphical one, box plot. Now, if your data is non-random, if data is non-random, use Kruskal-Wallis instead of ANOVA. That's the basic thing that you got to keep in mind. We'll do some of these tests. We'll understand it automatically. First, let's understand what is 2 groups and what is 2 plus groups. We'll know what test to be used. Let's go back to data. Now, that's my categorical X. How many groups do we have here? How many groups do we have here? 4 groups. Yes, absolutely. I have got 4 groups. I have data for Jaya, I have data for Nitin, I have data for Ravi, and I have data for Vandana. So 4 groups, which is more than 2 groups. So I will do ANOVA for this. Way Anova will be used because it's 2 plus. More than 2 groups is ANOVA. Perfect. Let's look at this one. Gender. How many groups do we have? Would this be ANOVA or which one? What is the name of the test? Anyone recalls what we discussed? Which will be the
Two sample test.
perfect, perfect. Two sample t tests will be used for this one because there are only two groups, male data and female data. So when we want to compare male and female data, two groups, I'll be using a two sample t. Let's check the second one. Next one. Which test should I use here?
One.
Perfect.
Anova test.
ANOVA test. Yes, one way ANOVA. Let's have a look at this one.
Two sample.
Sample test.
Perfect. How about this one?
Anova.
Graph.
Anova.
It is a title number.
Just think about the name of the test. We discussed about this already. What is the name of the test?
Here, I think that is not random. So we'll be going with Kruskal.
Kruskal. Okay. Just think about it. Is it categorical data?
Yes, it's a categorical.
Just think about it. Is it a categorical one? Categorical is text based. Is it text based? Is it a text based data? This is not a text based data. This is not a
Numeric.
text based. This is numeric data. Numeric data. What test do we do? Correlation test. You have to look at the data type. Data type is numerical. That's the rate. This test will be done on correlation. This one, what is the name of?
Very.
Absolutely, it says numerical. This will be correlation. This will be correlation because numbers, numerical X correlation. How about this one?
It's a graphical.
Text
Categorical.
one. Yes, yes, categorical. Which test?
No.
Absolutely, it's ANOVA. More than two groups. You're comparing more than two groups. So technically, when you're comparing more than two groups, it's ANOVA. When you're comparing two groups, it's two sample T. And when you're looking at data, which is all numerical, you do a correlation test. Simple as that. And so bottom line, what you're trying to understand here, what test do we need to do? We're comparing, say, we're comparing two groups, then use two sample T. When you're comparing more than two groups, you do ANOVA or Kruskal-Wallis depending on randomness. And this is if X is number, then you use a correlation. So based on the data types, you will end up choosing the test. See, it's very important to select the right test. Doing the test is not a big deal. You will do two clicks and your job will be done in two clicks. That's how easy it is to do it, the analysis. Now let's have a look at two sample. Let's first do the two sample t test, understand how to do this test, how to do in the interpretation of this test, and then we'll take it forward. Let's check it out. Two sample t. The path is start, then the basic statistics, and we go down to two sample t. Two sample t test is what we're comparing. Now, this section, samples will contain my Y and sample IDs will contain my X. What is my sample Y here? And I click, my ticket closure time is my problem, the business problem. Okay, select the ticket closure time, that's my Y. What is my X? I'm doing two sample T. So I'm comparing like gender, male, female, two groups, gender of the ticket handler. Well, what is my null definition? I have got female, I have got male. So my null definition says the average ticket closure time of female is same as average ticket closure time of male. They're same. Alternate says no. There is a huge difference between their performance level. Let's see. We've got the test done, and that's where we first look at it. P-value. Is it not? Are you going to go with null or are you going to go with alternate? Null or alternate? Mhm. You can use the chat option also. Like, sorry, didn't get
Null.
the voice. Null, is it null?
Alternate.
You can use the chat. At least I know who's sharing that, so at least I would be able to know who is not getting it correct. Null or alternate? You performed your test. Is it null or is it alternate? Chandan says alternate. How about others? Vaibhav says alternate. How about others? Please pitch in. Your p-value is right in front of you. We already done the exercise around the p-value. P-value is 0. So what do we go with it? Or do we go with null or do you go with alternate? It is alternate. Perfect. Yes, it is alternate. And so thanks. Nobody said null here. Yes. P-value is simple logic. Just ask a question. Is it less than 0.05? Simple logic. Is it less than 0.05? Yes. Then it's alternate. So yes, what we wanted to prove that there is a difference, and yes, I'm not being gender biased. Well, definitely, yes, there is a huge difference in the performance level of male and female. So people who were saying, well, I do not wanted to come and say, well, there is an impact or there is no difference. No, we collected the data. We have a statistical evidence which confirms there's a huge difference between the performance of male versus female. So it's not like a being gender biased, but yes, we have a statistical evidence for the same. P-value confirms there is an impact. Yes, there is a difference. Let's see who's good and who's bad. That's when we go and look at female, the 80 values in the data with an average of 17.24. So females are taking about 17.24 minutes to close an IT ticket. Male has 101 samples and an average of 19.75 minutes. Now, technically, it's time related data. Lesser the better. Females are doing a great job. They're taking lesser time. Now, the question, and that's how, see, all statistical tests work. This question, generally, when we do this test, can't we look at these averages? I can do it on Excel also. I can calculate the average of these 80 female data points, get the average of male. I know females are doing better. But the question is, that's what you've got to keep in mind. That's how every statistical test works. When we perform any test, the question is, do you see difference in the group averages or group means? First question, do you see there is a difference? I'm sure if they say the answer is yes, you see, yes, I do see there is a difference in group averages. Females are taking lesser time and males are taking more time. Yes, but is that relatively large difference? Can it be called as a statistically significant difference? Is it a big difference? Well, that's a question that I need to understand. Well, I see a difference, 17 minutes, 19 minutes. There is a difference, yes. But is it a relatively very large difference? Can I call it as a absolutely like the two poles apart, statistically different? That question. Second, other than this, what if I increase the sample size or decrease the sample size or change the sample altogether? A, you know there were 80 samples for female, 101 samples for male. I'm sure when you pick up a new sample or you add sample, you decrease the sample, these averages will change when you have these values like 8, 17 something. So you have for 80 values, you're getting this average, 100 values, you're getting this value. If you increase the samples, the averages will change. If you decrease the samples, the average will change. Average will not remain exactly the same. Or forget about it, you had a process from which you picked up this sample. So if I just pick up a new sample altogether from the same process, the question is, if we increase the sample, we decrease the sample, or we change the sample altogether, will you still see the same differences? That means basically large differences. Are these differences real or just by chance? Who will answer these questions? That is going to be answered by p-value. P-value, when you look at it, that confirms that yes. Looking at p-value, well, first question, do I see a difference? Yes. But is this difference a large difference? Can I call them at like statistically significant difference? What if I increase the sample? What if I reduce the sample, change the sample? Will you still see this relatively large difference? If it is a relatively large difference, are these real differences or just a matter of chance? Now, that answer is provided by the p-value. No, these differences are real differences, and the difference you see is relatively very large difference in their performance level. And you can say they are performing at two different levels. Females are doing a much better job in this process, and males are not. So technically, you know who's good and who's bad. And it's not matter of the sample, it's about the entire process. Keep this in mind. This is descriptive statistics, which you can do it on Excel. This is about population average. If you remember the symbol, if you try to recall, this is, so my bad, well, try to this is average of the population, mu. Looking at the sample averages, which is X bar, looking at the sample average, now you're predicting about the entire process. It's not about this sample. The question is not about sample. We were never interested in sample. We always interested in the entire population, entire process from which you picked up the data. So what if I increase the sample? What if I change the sample? I pick up a new sample from the process. Can you make a claim about the entire process? Yes. I can say this, these people in this process, from whichever process you picked up the data, females are relatively much better as compared to male. That's how we understand, read, and interpret a statistical test. And p-value is the evidence for that. Is that making sense to everyone? How to read, understand, analyze this? Is it okay, everyone? We'll perform other tests also, but yes, just want to make sure that we can read the data. Is it okay? Okay, I guess so. I don't get any other responses. So so I assume that we are all good with it. Yeah. So let's do a test for something else also, just to kind of check more on this two sample T stats, basic stats, and then we go to into two sample T test. My problem is still the same. I look for two groups, some more excess, which are two group. I've got shift related root cause. There's only two shift, morning and night shift. Let's see. Uh, I'm doing the test, Anupal. So I'm just doing this test once again. So some more test on two sample T. Do I see a difference? Yeah. Is it a relatively large difference? Well, there is some difference, but I can't say is it relatively large or not. What if I increase the sample? What if I change the sample? All those questions, technically, that's coming in my mind. Can you say they are absolutely performing at two different levels, morning and night? Null says no, they are same. Alternate says no. There is a significant difference. What is this value, null or alternate?
Null.
Null. That means, sorry, you wanted to prove that morning, night, they have a difference in their performance level. Sorry, we do not have enough evidence to support your claim. We fail to reject the null. That means they both are performing at same level. Morning shift, night shift, they're same. Don't come back and tell me that shift wise there will be impact on the productivity. There's no impact in productivity by the shift, be it morning shift, night shift. Productivity doesn't change. Shift wise, the productivity is same. We do not have evidence. If somebody says that morning people are more productive, night is not productive, no, sorry, that's what data doesn't speak. And I'm talking about entire process based on the data that we've collected. We've done the analysis. Based on that, we are getting the predictions done. Sorry, as of now, we do not have evidence to support your claim. Your claim is rejected. Null will stand true, and yes, there is no difference in the population averages of male or what of morning shift versus the night shift. Their averages are same. Let's look at some more examples so that just we understand this clearly. Two sample T back again, some more two groups related data. We got like process complexity. We have two levels, level 1 and level 2 sort of thing. That's how it is. Let's check it out. We got tier 1, tier 2. So level 1, level 2 process. How complex is the process? Do I see a difference 18.10 and 19.05? Yes, I see a difference here. What if I increase the samples? What if I reduce the sample? What if I change the sample? Will you still see the difference if it is a relatively large difference? Will you still see that kind of difference if we do that? Well, sorry, null. The difference you're seeing is not a relatively large difference. Hence, we cannot safely conclude that uh, complexity wise there isn't a difference, be it a tier 1 level 1 complexity or level 2. They're more like performing the same thing. This difference you're seeing could be just a matter of chance, like here and there. It's not a big difference. You can't claim that they are different. These are two relatively big differences. No. So process complexity wise, process that both the levels are working at the same level. So null means no differences, they're same. Let's look at something else again. Let's see if we have something else to deal with. We have any ticket type. I would need the answer from you all this time. Would that be a null or would that be an alternate?
Alternate.
Perfect. Which shift is doing better? Which type of ticket is doing better?
Network issue.
Absolutely. Network issues, I see a difference in the averages? Yes. 20 minutes versus 16 minutes. But is this a relatively large difference? P-value confirms yes. It is relatively large and you will always see the difference. You go and pick more samples, you pick up a new sample, you will always see a difference, and these differences are large enough. There is a root cause, yes. Ticket type is a root cause, definitely yes. So that's how we do the two sample t-test. Is everyone okay with it? Everyone is okay?
So this question which comes in our mind, that should we select some more samples, or should we, do we really do that, or
No, it's basically that's how we try to understand. Like, see, technically, there could be a question which would come into mind. Like, I do see these are the questions how we interpret p-value answers this for all these questions for us. So we don't go and collect more samples. Technically, see, if you have done a sampling correctly, if your method of sampling is the same, so 100 sample will still give you the same answer, and 200 sample will still give you the same answer. That is what we're trying to say. If you've done your maths correctly, the sampling process, everything is correct, then your data, this small sample is giving you accurate prediction about the entire process. So even if you increase the sample, reduce the sample, you are going to get same conclusive evidence. So that's how, so these are the interpretations of that you try to understand how this p-value, what is it doing. Technically reading the descriptive statistics, and then based on that differences, it is predicting, is this a significantly large impact? Yes. And that's how it says yes, it is a significantly large impact or not. Okay. So we don't ask this question, but technically that's what it means. Even if you do any of these, should you want to do it, you will still see the difference. That's what it says. If you still do all this, you increase the sample, you reduce the sample size, you change the sample, still you will get the differences, and significant differences. And that's what p-value is telling you. So that's how the two sample t-test is done. Like, if you have any two groups that you're comparing the average of two groups, please do this kind of test, the two sample t. Now coming to ANOVA, one-way ANOVA, when we have more than two groups to compare and take a decision. We'll talk about Kruskal-Wallis later once we're done with the ANOVA part. Uh, well, if I'm dealing with ANOVA stats, then we have ANOVA. There's a third option. Then we have one-way ANOVA. We click on one-way ANOVA here. Response, we put in the ticket closure time, that's my Y, and factor is my X. I have more than two ticket handlers, like, so I will use ticket handler as my X. So Y comes here, ticket handler comes as X. So Y and X. In ANOVA, we have an extra bit of more testing. Like, technically it brings more clarity. We click on comparison and we select Tukey. Now, Tukey comparison is the best one. It enhances the clarity of ANOVA. So we'll use this, select this one, and we'll see how good it is. It's very meaningful, easy to understand ANOVA. In that case, you have using Tukey. We did ANOVA. Null says all means are equal. Everyone that you're comparing, all the ticket handlers are same. Alternate says no, not all of them are equal. There is a difference, and the difference is a large, statistically significant difference. You have four ticket handlers: Jaya, Nitin, Ravi, and Vandana. There are four groups that you're comparing. What does this p-value tell you? Is it null or alternate?
alternate?
Absolutely, yes, absolutely. So is this a root cause?
Yes.
Absolutely, it's a root cause. Alternate means it's a root cause. Yes. So definitely there is a significant difference in the performance level of different ticket handlers. This is not minor, a major difference in the ticket handler performance. That's what is confirmed by the p-value. Let's understand who is doing how. Like, so if there is a difference, who is good and who's bad? Let's see that. Let me get the annotation option back again. So I know there is a difference. Jaya has 22 samples. Just look at this, 22 samples in the data. She has an average of 19.19 minute. With 95% confidence, we are saying that based on her data, she would generally take about time to close the ticket in range of 17.7 minutes till 20.6 minutes. That will be the range of her ticket closure. Sometimes she would take it lesser, sometimes she will take it more, but that will be the minimum and maximum range of her ticket closure time average. Nitin has 56 samples and has an average of 20.6, and his ticket closure time range will between 19.7 and 21.5. Ravi has a 45 samples and he has got like 18.6 as an average. His ticket closure time will range between this and this. But if you look at Vandana, she's league apart. Absolutely different. Let me get rid of this stuff. Look at this. She ends at 17.4. They don't even start at 17.4. This is where Vandana is my role model. Lesser the better. She is she is phenomenal in her process, the average, and her ticket closure time ranges between 15.5 till 17.4. Maximum she would take is about 17.4. These guys don't even start at 17.4. She is a role model for everyone. Okay, forget about Vandana. Even if you don't have Vandana in this game, you'll still get an alternate. Why? If you look at Ravi, his data is at 19 point, ends at 19.6. This gentleman starts at 19.7. They don't overlap. There's nothing in common. This ends at 19. So this is ending here, and this guy is starting here. So one guy has a range of this to this, another person's range is this to this. They don't share anything in common. They have two different poles. They don't. So if I talk about Vandana, she is any which is different from everyone else. Nothing in common with anyone. So that's what this table helps me understand. So Vandana is my role model definitely. But let's get an understanding clarity here. How to read the Tukey. If you remember, I talked about Tukey. Means, it says averages that do not share a letter. If you see a different letter, then they are statistically significantly different. They are very different from each other. If you see a different letter. So what Tukey does, it gives an alphabet. Based on Nitin's data, it has given it an alphabet A. Okay, your data looks like an A. So putting you in a group A. Jaya, your some data looks like A. So you also have a feature of A group. But your some data doesn't meet with the A group. So we are putting that as group B. So you have two types of data. Your data has both the feature A type of data, which is similar to Nitin, but B type of data, which is not similar to Nitin. So some data is different from Nitin. Ravi has only B type of data. So here, so Jaya has both features of Nitin and Ravi, and Nitin and Ravi have nothing in common. Nitin and Ravi, they are absolutely two poles apart. We checked it. Nitin and Ravi, two poles apart. He ends at 19.6. He starts at 19.7. Hence, A and B, two different groups. But Vandana, she is anywhere like absolutely away from everyone else. So this is why if they are significantly different, you will see different letters. If they are, you see, if there is a very simple way to understand, if you see everyone A, that means you will be null. Every time when you say null, you'll see everyone with A. That means there is no difference. Same group data is put in one alphabet. So if you don't see any other alphabet other than A, it will always be null. So here we have A, we have B, we have C. That means there are different groups in the process which are performing at different levels. Let's look at some more example. It'll get clear. Let's pick up another X which has got multiple levels. Let's say ticket handler age group. We had three groups. Let's see. Is it null or alternate? Please help me understand. Null or alternate? Is it a root cause or not?
It's null.
Null. There is no evidence. Sorry. You wanted to prove that probably younger people are faster Older people are slow. Sorry, we do not have evidence to support it. Your claim is rejected. So our understanding is that everyone is performing at same level, whether it's a young person or medium age or probably older person, everyone is at the same level. We do not have any evidence for that, for whatever claim you were making. If you look at them, these guys, they have like more like same. If you look at these, if I kind of plot this, say 17.5 is here till 20.8, 17.5. So this is also static. So there is a lot of overlap. They have something in common with each other. Everything like they have some overlapping. 17.8 somewhere here till 19. So they are all overlapping with each other. Everyone. If you look at Tuki, it will everything put everything in one group. Let's look at Tuki. AAA. Absolutely same. There's nothing in different in them. But if I look at similar tests, say if we do it for something else, let's see. I'm not sure whether which one I will get another difference. Let's say we have got a qualification. Let's see, we get this one qualification. Is it null or alternate? Is there a difference in the productivity level of graduate, postgraduate, undergraduate? Do you see a difference there? Is it null or alternate? Others, like if I just got to hear it from one person.
Null.
Null. P-value confirms there is no statistical evidence. So be it a graduate, postgraduate, or undergraduate, they will be all performing at same level. And let's look at this. AAA. We'll look at some other example, just for an argument's sake, so that we are clear about it. Let's use trainers. Some trainer. Null or alternate?
Alternate.
Alternate.
Perfect. Let's see who's. Let's look at Tuki. It makes the job easier. Who who all people are not matching with each other?
Sam and Rajesh.
Sam and Rajesh. Perfect. Sam and Rajesh. Sam and Rajesh. Sam has been put into group A and Rajesh into group B. They're performing it. So the differences are real differences, and these are statistically significant difference between these two people. So that's how we look at ANOVA. Is this okay with everyone? ANOVA, everyone? Are we all okay with ANOVA?
Yes.
Okay. Just want to check with everyone. Uh, do we have MINITAB? Anyone is there who doesn't have MINITAB installed by now? Because I would definitely want to hear it from you. There's certain data for you all to kind of look into and practice also. So, okay. Uh, we'll be sort of giving a short, not like a break for myself, but a work for you or people who have got Minitab. So we'll be parking it for quick 5 minutes, and I'm going to show you the data. Please do the test just to learn it and understand and tell me. Okay, whosoever doesn't have Minitab, I'm going to do that. So probably you'll have to wait for 5 minutes while somebody else does it, and we will be kind of practicing it parallelly also on the same data. So uh, anyone who doesn't have the Minitab can get it installed for future. But yes, just try it out. The data for practice is here. So data files for class. Uh, we will be doing it back, by the way, like anyone, whatever people are going to do. So I'm going to go on silent for 5 minutes. I'll be here only, but people who have got Minitab, please practice it. And I'm going to repeat it with everyone else. In the analyze folder, in the hypothesis test, well, I think 3 people don't have it. That's what I got to know from. So there are certain data that for you to practice. We've got 2 sample T data also. We've got ANOVA data also. We'll be talking about correlation and scatter plot stuff. Like that needs some bit of more explanation. But do open up this 2 sample T file and practice. Just let me know. I'm going to give you the data for you to look at and say there are 2 hospital ratings. Let's compare them. Hospital A and Hospital B. So we've got the customer satisfaction rating taken up by some customers. So we did some random survey. We surveyed some customers from Hospital A. They gave some ratings. We got some survey done from Hospital B, and we got their ratings also. Now this unequal doesn't matter, but we got some survey done. And we would like to understand whether hospital A is better or hospital B is better statistically. Do you have, if you have to recommend a hospital, which one would you recommend? That's what we'd like to understand here. So please do this one. That's one. And so I will, so people who do not have Minitab, please just stay there for a moment while others do it. So we'll take probably just pause for a good 2-3 minutes. And then for everyone else who has got the Minitab, please do test and we'll kind of verify this, whether you've done it or not. And then you have a data in, I guess, okay, we have got classroom. Okay, this one, the last one, exam results for green belt. We've got a classroom method and an e-learning method. So null says both method, whether you go for classroom or e-learning, your marks is going to be same. Alternate says no, there will be a significant difference whether you go for a classroom training or an e-learning training. We would like to understand whether there is a relationship or there is an impact of method or not. Say, so we are looking at the sheet number 5. I'm sure you all have the same sheet. So this is what we would like to you to practice on, the exam GB exam result for 2 sample T, and then the hospital rating, which is sheet number 2. Just work on it. I'm going to be on mute for a couple of minutes, like, so please try it. First we're looking at the hospital one. Anyone who's done with the hospital one, please share the p-value so that we know for sure that you have understood it, and then we'll move on just for a couple of minutes, and then I'll take it up. I'll do this and then we'll move on to the other one. So I'm going on mute for a couple of minutes. I guess more people who don't have Minitab now. So okay, let's then do one thing. Let's park this. Let's kind of do this test and understand how it's done. So probably that, otherwise people will keep waiting. Let's do the test. We'll come back and do the correlation stuff also, like, so we know how the test is done. But let's quickly understand. So these are the 2 hospital data we want to do and check the test and understand which hospital is a better hospital, or is there a significant difference in there? Them or not. So stats, basic stats, 2 sample T. My rating data is here. The hospital will be my X. That's it. Click OK. Let's look at the p-value. Now help me understand. Is there a significant difference between them? Is it a root cause? Yes. Who is the better? Which one is the better hospital? A or B?
B is the better one.
We've got an average ratings here. Average of the customer satisfaction rating. A hospital customers have rated it 80%.
A is the better one.
A is the better, highest customer satisfaction rating. So that's how we simply test it. Let's kind of quickly check the other one also. We have this file, say the green belt exam versus via classroom method or the e-learning method. That's what we would like to check. Let's go and quickly check this out. Whichever mode we are going to work with. So stats, basic statistics, and we've got a 2 sample T. So we go and to the exam results as my Y, method is my X. Well, let's see whether there is a impact or not. Would there be an impact? Is it a root cause?
Yes.
Absolutely yes. Which one, which method is a better one?
Classroom.
Classroom. Perfect. So Yes, this definitely tells you that there is a always a higher, better advantage if you go for a classroom training. You score more versus an e-learning. That was probably the mindset people. But now says that it doesn't matter. You go through classroom or e-learning. Technically, learning will still be the same. You will be able to get similar stuff. But unfortunately, statistically, we have a statistical evidence now which will reject this null, and now we can say with conviction, no, there is an impact, and impact is not a small one, a significant difference in the classroom scores versus e-learning score. So nothing gut feeling based, it's coming from data driven studies. So that's how we do the two sample T. So similarly, we have these tests for ANOVA also, some practice tests for ANOVA. So let's quickly have a look at ANOVA also. So we've got the data, like so again, says now we have got more than two groups. So we've got marks obtained through various methods, online, lecture, demo. So there are different section ways how we take the training, and there are different marks that we've got. More than two groups. So we will be doing ANOVA for this. Let's do ANOVA here, and same logic starts ANOVA one way. We select the Y, which is the marks, and we select the X, which is the mode. Comparison, we select the two key, and then click OK and OK. Is there a difference?
Yes.
Yes, that's a root cause, and it tells you which one has got like a best one. The demo, I don't know what method is that, but demo method has been scored high in the group. Every method is significantly different from each other. The best one is the demo, second is the lecture, third one is online. You scored lowest in online, then the lecture. God knows what's that and what's demo, God knows. But yes, that's how technically that's how we test it. I will. These are the tests which is used globally for testing any like three groups. When you have more than two groups, you always use a ANOVA method. Now, having said that, can I do this test on Excel? Yes, we can. So that's sort of, I don't think there should be any limitation for anyone to do this test on Excel. We all can do it, and please just keep a note of it. And so for two groups, we need, in case of Excel, you need data in this format, like two groups. What we were generally having it like this. So all the Y was in one column, and X, both X was in, they were in two columns, like the same column. A and B was in same column. But when you're using Excel, you need to have data like this, all A data in one column, all B data in one column. That's how the data needs to be plotted in Excel. uh, so people, everyone has Excel. I don't think everyone, and nobody would be there who would not be having Excel. But for analysis, the statistical analysis, you have to activate the Excel plugin, which is data analysis plugin. For that, please do this activity. File, you have options here in the options tab. When you go to options, it will give you an option of add-ins. You go to add-ins here, it will give you here, you will generally be seeing analysis toolpack. Mine one is activated, so you will generally see it here. You have to click on this, click on go, anything. So whatever is visibly, when you click on go, it'll open up this box for you. What do you want to add? So I have only added, I'm not using VBA. I only added the analysis toolpack. That's it. I checked this box, I clicked OK. The moment I click OK, when I go to data, I will be able to see this data analysis tab. Now let's click on data analysis tab, and it says, remember, two sample T test. So two sample T test is, we have an option of T test, which is use two samples, comparing two samples, assuming equal variances or unequal variances. Technically, there are two options. We can look at standard deviations. We can see if they're very, very different. We can all directly go with this assuming unequal variances. That's what MINITAB also uses, unequal variances option. We click on this. Now we have to select the first data. Let's quickly have a look at this first data. But there are limitations in Excel, so you will not get all the tests to be done on Excel, but whatever is applicable, please see. That's what we can work on. This is first data. Where's my second data? My second data is here. So first data and second data. I have selected along with the labels. You have to check this box also. You have to keep it on, because you have selected, I have selected from the top, so including the label. And then alpha value, what are we working with? 5% of alpha value. 5% is what we work with, 0.05. That's what we have. Click OK. You can look at the test results. Now, the two p-values we're getting. One is a p-value, which is this one. And this is one p-value, another p-value. You can see this one. Technically, what we are interested in, the second p-value, which is what we're trying to say, there is a difference. So when do we use one-tailed? When you want to prove that it is more than, so this is more than or less than, is when we look at one-tailed. So if we want to prove that males are better than females, or females are better than males, when you want to prove male greater than or less than criteria, that's when you use the look at one-tailed tests. But when you're dealing with a two-tailed one, technically we just want to prove that these two groups are technically different. These two samples are different that we're dealing with. What did we do? Hospital ratings. They are two significantly different samples. That's when we are talking about two significant, which can be more or less, but they're different. That's when we look at two-tailed tests, and that's what it tells you. 0.00. That's your p-value.
Can you tell me the steps again, please?
To do the test or to add in?
Yeah, to add in.
Okay. Let me just delete this then. Okay. Go to File. Go to Options. When you go to Options, click on it. And here in the tab, you'll get add-ins. Click on add-ins. And you click on add-ins, you'll see a lot of stuff, inactive application add-ins. Generally, your analysis toolpack will be here. So click anything. When you click on this thing and click on Go. When you click on Go, you will see this box coming up. Here you have to select it. So I want analysis toolpack. Click on it and click OK. Now the statistics tab will come up here. Analysis, data analysis. These are all a lot of statistical tests, like not everything, but very limited, but yes. So whatever is there, we can still use it. There are certain tests which can't be used on Excel. Unfortunately, Excel is not a great statistical tool, but whatever is applicable, we can still use it. It can solve a lot of things for us, definitely. Is it okay with everyone? How to add in? Okay. Now, once you have done this test, let's me quickly try and do it for something else also. Say we want to try to understand whether there is a difference in average of in-house audit scores versus external, the customer audit score. Now it says no, they are same. Alternate says there is a difference. Let's find it out. Data analysis. We generally go with assuming unequal variances so that we don't, otherwise you have to first find out the standard deviations, compare whether standard deviations are same or not. So this is what MINITAB also uses without using unequal variances. If you look at it, two sample t-tests, variances are not assumed. Equal variances are not assumed. That's what MINITAB also uses. Safest, cleanest. Click on it. Okay. Now, first data is first tab. Pick up the first tab from the header. Second data, click on this from the header. Both the data has selected. Yes. Do ensure you check label because you already picked up the label in-house, and so that has to be there. And that's it. Click OK. You have got your p-value. And remember, two groups we're comparing, we always look at two-tailed test p-value. This is the p-value that we have for this. There is no difference. We do not have any statistical difference to confirm whether there is a difference in the audit score of client versus ours. We have same audit score, like so. Internal audit score and external audit score, the customer audit score, we are same. So that's what p-value confirms, null. Is that okay with everyone? Shall we move on to the next thing? I'll just show you the ANOVA also because we have to do ANOVA, the Excel one version, ANOVA. So that's the two sample. So you can do a two sample. You don't need, if you don't have MINITAB, doesn't mean that we can't do it, but yes, there will be some limitations that will come across. You will be able to see what's the limitation here. Like not everything is there in Excel. It is picking up, God knows by when. It will take time. So you can't do the test like this method. You always have to kind of get in multiple columns. That's how you have to. You can't, like MINITAB, you can put it like this. You can do the test, but you need to have data in multiple columns. Let's do the test for ANOVA. Let's pick up for some. You can't do it like this. Okay, we can do it for this multiple columns. Let's use this one just for argument's sake. Go to data, same process, data analysis. Go on the top, the first one. It says ANOVA, single factor. Yes, that's my single Y. We in Six Sigma generally work with a single Y. Single factor. Click on one way ANOVA. That is what it means. One way single factor. What is your data range? Well, my data range is all this. This is my data range. Click OK. Labels, yes, we have labels on the first row. 0.05 alpha, that's all. Job done. Click OK. That's your analysis. You don't get 2 key and all that stuff, but yes, still you get your p-value. P-value is what we're looking for. This is alternate. Keep this in mind. How to read this? This is E minus. So this is like, this is followed by, so this is what this value is, 7.6472 6 divided by 10 to the power 11 zeros. So 1 followed by 11 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. This will be less than 0.05. If you divide by these many zero, it will be less. So this is alternate. There is a significant difference. That's what you're able to understand from p-value. E, that's when you see E exponential. This is exponential 11. So that means it is alternate, less than. This is not null. E, the moment you see E, that means it's exponential. That means you have dividing by 10, those many zeros. So here we're getting the same stuff. We get to know that the lecture mode is great. There is a significant difference. Yes, alternate. Let's look at something else also. We'll get to see for this one. Say data analysis. I want to compare different samples. Are they same or not? So I go and say different samples. Unequal samples, it doesn't matter. Unequal is fine. You can use this. Don't need to have labels. That's fine. Look at this p-value. That's straightforward. Null. Null. Are we good with these? Excel testing? Is everyone okay with it? It will be great to hear from you all.
Yeah.
Perfect. Okay, let's then move on to the next test. So we will be able to, so barring that, now let's come to the limitation here. You can't do run chart there. You can't do the run chart. So you can't check whether ANOVA is fit or not. You can't do that. You can't do Kruskal-Wallis on Excel. You don't have that option. So there are limitations, yes. So I would not know whether I should do ANOVA or not on Excel, yes, because I cannot check this. There's no direct formula or something like this unless until you have an Excel paid plugin which can help you test normality on Excel. That's the second. Limitations are there. So yes, these are free stuff which is available. So, but yes, there are certain things which can be done. You don't have the normality test direct function here. No randomness test function here. You don't have Kruskal-Wallis test. You can't do it. So yeah, you have two samples. You have ANOVA. You have got correlation. Yes, we do have option of these tests, but limitations are there. Now, keeping in mind the data is normal random, we have done ANOVA, but if the data would have been non-random, if it would have been non-random, if we would have found some patterns when we did the testing, then we would have done Kruskal-Wallis. So Kruskal-Wallis, let me quickly show you how to do Kruskal-Wallis in case instead of ANOVA. Stats, non-parametric. This is a non-normal data test, non-parametric, and you go down to Kruskal-Wallis. This Kruskal-Wallis is going to compare medians. The data, even if the data is normal, it's going to compare medians. Why? Because data is non-random. There are issues in the data, there is patterns in the data. It is going to study the median of the data. When you did two sample T, you compared averages of two groups. When you did ANOVA, you compared average of multiple groups. Here, you're going to compare the average of medians of groups. Response is your Y, factor is your X, mode of the study. That's what you do. Click OK. There is, you generally go with adjusted for ties. If there are any errors, they generally see, if they cancel out something, like, so it's actually good for adjusted for ties. Generally, they will be the same. So this is alternate. That means there is a significant impact of the type of mode that we go for. So yes, there is an impact. Definitely, yes. There is a median wise, there is a huge difference in there. So it is comparing the medians. It's comparing the medians. Null says all medians are equal. Alternate says no, at least one median is different. We get an alternate, which confirms that there is a difference and statistically significant difference in the scores that you obtain by different modes. And we know highest you can get from demo versus the lowest is the online one. Are we good with this, everyone? How to do the Kruskal-Wallis one? Like if you are okay, we can move ahead.
Yes.
Okay.
Yes.
Rather, like let's ensure like should we take the quick 10 minutes break right now and then we be back in 10 minutes? Is that okay with everyone? Because uh,
Yes, sir. Yes,
okay,
sir.
okay. Let's then be back in 10 minutes from whatever time zone we are in. Please be back. Are we back from the break? I would request you to please confirm in case we're back. Okay, perfect. How about others?
Yes, sir.
Okay. All right. So we covered this segment of the test. We will be covering up the correlation and the scatter plot. Please, I hope we all recall how do we use box plot. In case we don't recall it, I'll just do it so that we whenever we did these tests, either a two sample t-test or a ANOVA test, or for that matter, Kruskal-Wallis, the box plot will be the graphical tool generally which we use for like a graphical representation of the test. So A, we had the test results. B, we will have the graphical plot. So say if I want to do a graphical plot for this one, so I go to box plot, I use with groups, and I click OK here. So I get to know this is my Y. This is where my X will go. So exam results, that's my Y. Categorical variable is the method through which I do the test. And that's it. We click OK to get to see the box plot. So similarly, I will be able to perform the box plot test, and if there is any criteria for box plot as a minimum passing percentage and stuff like that, we can also add it in the reference line scale. There's some target which has been given by the management. Say we have a target that at least we should get, say, 75% marks. So that's what I'll put it in reference line. Click OK, and then my box plot will have a line of target. And just by looks of it, I would be able to understand what percentage we're doing good, what percentage we're doing bad. Technically, in this case, my classroom is doing much better as compared to the e-learning. I have like a 50% pass and 50% fail. Median is the center of the data. So 25% is in the tail, 25% is the tail. So 50% is fail and 50% is pass. So if I look at this 25 is pass, this box has 25%, which is pass, and this box has 25%, and more like it's like bisecting midway. So 12.5 here and 12.5 here. So I know 12.5 is pass. So 12.5 plus 25 plus 25, about 62.5% is pass when people take a classroom training as compared to 50% pass. That's how, just by looks of it, I can also do that interpretation, and that will be backed up by the statistical test that we use. So that's how we combine these, be it any test out of these, we use a box plot for a graphical representation. Now coming to correlation, the reason why we packed it for later stage was because there is some bit of more stuff that we need to know about correlation test, which will add more flavor to what we are trying to learn. So correlation test gives you some extra information. So when you do correlation, it gives you an R value. This R value is called Pearson's correlation coefficient. Now, Pearson's correlation coefficient, what does it do and what does it mean? A, I get a p-value, definitely. P-value will always come. So p-value logic doesn't change. When we look at p-value, what does it tell you? It tells us if x is related with y or not. That's what it tells us, if x is related with y. Now, Pearson correlation tells you two things. The R value will give you two things. It tells you how much is the impact. They are related, but how much? Is it like a very strong relation? Is it a weak relation? Is it a medium relation? But it tells you how big is the impact of X on Y. Secondly, it tells you the nature of relationship. Let's understand what does it mean. So first of all, when I see an R value, the range of R value will be from -1 with a 0 in between. So that's your R value can be anywhere between -1 and +1. That's what it will always be, in between this range. So it could be anywhere between positive, negative. But when you look at R values, what sense do we make out of the R value? So first of all, we talk about the degree of impact. How big is that impact? How do we get to know? By looking at the value itself, not the positive, negative, but the value. If your R value is between 0 and 0.3, you have a negligible or no relation or no impact technically. It's very, very nominal or no relation, no impact at all. If it is between 0.31 to 0.75, we'll say there is a medium impact or like a average impact sort of thing. And if it is more than 0.75, then I will say there is a strong impact. X and Y are very strongly related with each other. So that tells you the degree of impact. Other than that, the nature of relationship is what we also want to understand. Nature of relationship. Now, nature of relationship, you will not get to see this positive sign. Positive you will not see. Positive will just appear as number, but negative will come with a negative sign. So positive or negative relationship. What does it mean? If there is a positive number, a number like 0.3, this is positive. There is no, you don't need to put a plus here. You understand it's all positive. So we see a number as it is, that means it's a positive relationship. What does it mean? If positive, if X increases, Y increases. This is a positive relationship, directly proportional. If you see a negative sign in front of R value, that means if X increases, Y decreases. There's a negative impact of X on Y. So let's take some examples of how your R value could look like. So some sample numbers just for R value: 0.21, 0.56, 0.89. Well, is it positive? Yes, I see all that as positive. I don't need to put a plus sign, so technically it's a positive. But this falls into 0 to 0.3. This is negligible. So I'll say negligible or no impact between X and Y. This one falls into the medium zone and a positive one. So I'll say I sort of moderate or medium positive. So medium positive relation between X and Y. This is in the strong zone. So I'll say strong positive relation between X and Y. So debate based on the number. I could get number R values as minus 0.26, minus 0.63, minus 0.88, some values. Is it as per the impact? Well, I see it's negligible. So negative sign doesn't matter because it's still a negligible impact. Positive or negative doesn't matter because it's negligible, almost nothing. This one, yes. So I'll say medium negative. And this will be strong negative impact. So that's what R value will indicate. So we got to keep this in mind. R value is going to tell me how big is the relationship and what is the nature of relationship. P value will just tell you, is there a relationship or not? Generally, when you get a P value, which is null, you'll always find this one. So generally, P value will be here. This will be the value of R value. R value. This is what you will see. P value corresponding to this will be null, alternate, alternate. Whenever there will be an impact, you will always see alternate. There is a root cause, yes, and there's a medium or strong relationship. Negligible will be null. No relation, negligible. Technically nothing, no relation. Similarly, in this case also, same logic. Positive or negative, but technically, when you see an alternate, that means it's the root cause. It is positive or negative, doesn't matter, but there is a relationship. That's what we will generally see when we do a correlation. Let's look at some examples and understand the correlation also. There's a data for correlation scatter plot in the same folder. We open this up, you will see some different files. So let's have a quick look at the file. We go to the data here and let's add in the data. So let's copy paste this data from correlation. This kind of data is maintained by all the confectionery industries, like beer industry, any kind of industry, say, which was dependent on temperature. So like you can have any data. So you can have two data. One is under Y, another is X. So we'd like to understand, are these correlated? Is temperature influencing the sales or not? So if my business is related with the climate condition, Well, I would like to record my daily sales figures, and I would like to record what's the daily temperature, and like to see, is that impacting my Y or not? So X has to be number, Y has to be number for me to do a correlation test. So let's see correlation test. It'll give you scatter plot on its own. Stats, basic stats, and you go down to correlation. You click on correlation here. Now, you don't get two separate boxes here. You get just a single box. Both will contain X and Y in the same box. Now, ideally, we should put X first and then the Y. Temperature first. I want to check impact of temperature on sales. That's what I want to study. Click on results. Select this pairwise correlation table. That's what we want to check. And click OK and click OK. Now, there will be some bit of information that will come up. Let's check this out. Let's scroll down. P-value, null or alternate. Is there a relation between temperature and sales or not?
There is.
Absolutely, yes. It's an alternate. There is a relationship. How big is the relationship? That's your R value. Looking at that range, how big is the relationship? 0.9.
Strong.
Absolutely, yes. Strong positive relationship, right? So what it means that if my temperature increases, it will significantly increase my sales. Well, that's good piece of information to know. So let's see the scatter plot. This is scatter plot. And if I just let me blow it up, it is a pain to blow up this charts nowadays. If anyone is using an older version, these will come out of this automatically. MINITAB 17 will give you automatically, it will come out. It doesn't, you don't have to click on it. Okay, I will repeat it just a moment. I'll just, because we'll end up doing it again and again, like different kind of relationships. But just quickly have a look at R value, the same R value we see. This is for temperature. All this is for temperature, and this is for sales data. We see when the temperature was low, my sales was low. As my temperature increased, my sales slightly increased. As my temperature increases, if my temperature increases, my sales increases. If my X is increasing, it is increasing my Y. So there is a positive relationship. If X increases, my Y increases. There are coordinates. So if X is low, my Y is low. If X is high, my Y is high. Similarly everywhere. But at times looking at dots may not give you a very clear picture. So what we do is we go to add item. We go to regression fit. We'll be learning about regression next. Regression is related with correlation, and we'll understand how. So regression fit is what we click. Linear regression we look at, and we click OK. This will give you the direction of the dots. Now that's called best fit line. Best fit line, what helps you to understand what is the direction of the dot. A line going diagonally up tells you there is a positive relationship. It's increasing. That's what it tells you. Diagonally up. When X was low, Y was low. X increased, Y increased. X increased, Y increased. X increased, Y increased. If my temperature is increasing my sales. My temperature is less, my sales is less. The line going diagonally up will mean the same. That's the line helps you a lot. And if I take my cursor here, it will show you some bit of more information about this line, but thanks to what have happened with my system, and which is, let's see, let me just cross off this. Weird. Okay. Basically, if I use this, okay. If I end up, let me just try it once again. Better of using the older version, but again, generally people who will install MINITAB will get the latest version, and that's how it is. Otherwise, older versions, you have to do correlations separately. It doesn't come on its own. So graph, you have to do it separately in older versions. So regression fit is what we did. Get the regression line. Now, if I get my regression line, I click on, I just take my cursor here, it will show me some bit of values around this. See, regression fit equation, some values. It says R regression fit sales and some equation it gives me. And R square, some value. What is that? We will get automatically get to see when we do the regression test. This is correlated with it. Let's look at some more data because the regression can be, correlation can come in different ways. A can get a positive relation like this. So you can do a lot of testing like this. Say, a lot of people have conducted a lot of studies like this. Say, how many hours I study and versus what kind of marks do we get in the exam. That is some kind of study. Speed of the car versus the number of accidents that are happening. So you can do a lot of tests. You want to know what is the impact of X and Y. Both are numbers, do a correlation. Simple. You get to know it. Let's look at similar. So you can get anything, positive, negative. This kind of data is maintained by the second-hand car companies like who, the second-hand car market is getting bigger. They maintain such data. In India, we have this cardekho.com, carvecho.com, and stuff like that. So globally, second-hand car market is getting bigger and bigger. So they maintain the data. What should be the right price of the car and stuff like that, the mileage of the car. They collect data and information from various service stations to understand what should be the right values. So technically here we want to predict the mileage of the car as the car age increases. So we want to know X impact on the Y. Let's do a correlation here. Stats correlation is here. First the X, which is age of the car, then the Y, which is mileage of the car. We already have got results here, which is correlation stuff we already selected. Click OK. Now we will see a reverse trend here this time. Let's see p-value. It's an alternate. There is a root cause. Yes, there is a relation. Absolutely. There is a negative. It comes with a negative sign, minus 0.967. So there is a strong negative correlation. If my X increases, my Y reduces significantly. If age of the car increases, my mileage reduces significantly. As the car gets older, mileage reduces. That's what is shown in this plot also. If I blow it up, a line here, regression line, that's what we'll pull up. Regression line going down, diagonally down, means a strong negative relationship. The previous one was going up, this one is going down. When the car was new, the mileage was high, the car got older, mileage reduced. Add items, regression fit, and then linear regression. The line going diagonally down helps you understand the direction of the dots. The car was new, the mileage was high. The car got older, mileage reduced. Car got older, mileage reduced. As X increases, your Y reduces. That's the negative correlation. By the way, you can get other version also, which is, you look at this one. You could get anything. So data you don't control. When you get the data, you will test it and you get to see what kind of relation do you get there. So right now, we're just trying to see how different kind of data you could come across. So this is about hours worked versus salary, how much you earn given the number of hours you work. Correlation, we worked hours is my X. I want to check the impact on salary. This is already checked. Click OK. And here we got the this p-value. It's null. So no relation. Yes. If I look at this, this is between 0 and 0.3. Negligible. Nothing. That's what it tells us. Now look at this graph. Let's blow it up and find the regression line, which will give us a fair bit of idea. It will be more like a flat line. Line diagonal up is strong positive. Line diagonal down is strong negative. A line which is flat, which will mean no relation. Slight here and there could be there, but regression fit. Okay. More like a flat line. That's what you will see here. Yep, more like a flat line. When somebody worked some hours here, made some money like 23,000, worked 63 hours. Somebody worked 90 hours, made 49,000. Somebody worked 101 hours, earned less. Well, doesn't make sense. Somebody earned 169 hours, even made even less. Doesn't seem to have a relationship with the hours you're working in this data. Yes, that's how it looks like. So this data is all scattered here. Technically, there's no relationship which is evident from this one. So I failed to prove it wrong. Well, so technically I wanted to prove that hours worked is very strongly correlated with salary. It doesn't seem so. Well, it depends who is working, what's the pay scale. So different correlations can be there. Having said that, can I do this on Excel? Absolutely, yes. I can do it on Excel also. Formulas are very simple. If we do go want to do this, correlation is correl. Do this, pick up the arrays, select the data. You would have your correlation test done. Oops. Okay. I get ray 1 and ray 2. I have to select it separately. We can go to data analysis pack. That will be easier, but let's see. Let me try out. Comma. I have to do it this way. I was just trying to find a shortcut. Yes, that's what it is. That's the correlation R value we're getting. Let's look at the correlation test here. If I can find it here, I think it should be there. Correlation is here. Input range, you put the data here. Correlation is here. We go to labels are there. Yes, we've selected the labels. Click OK. That's what it tells you. Strongly correlated. Yes, that's what strong correlation between these two values. Is it okay with everyone, the correlation test? So pretty much with these tests being done, technically we complete the analyze phase, because our job is to kind of go through this data which we have collected in the measure phase, and we should have been able to complete this test by either correlation or two sample T or ANOVA, or for that matter Kruskal-Wallis. If your Y is non-random, you have to use Kruskal-Wallis. So you'll be able to finish up any data that you have with this test, and technically that will complete your analyze phase. You will know what's your root causes which is really impacting your business, and that's how we take it forward. Like, so we will wherever you have found that there is a root cause which is impacting your business, you will start working on them in the improve phase, because you've got your real root causes identified. We'll talk about analyze improve phase now, because technically we are, once you're done with this test, we hypothesis test in the your phase of like analyze phase, we already know the root causes. So we start with the improve phase. Now improve phase will also have some statistical tests that we will be covering up. Given the time, we are only going to be looking at like the first test, and we will be only able to cover the first one, which is regression. Regression test is most powerful test that we have in entire, like all the statistical tests. Now in improve phase, we've got the identified vital root causes, the real root causes. Yes, I do have them, but which ones are most important? Like, not all root causes will be equally important. Some excess will be very, very important. Some excess will be less important. So I need to know how important is every root cause that we have identified. Basis that, I will put my efforts on the excess which are more important. Will put less, like more effort, vice versa. So we will learn about two types of regression. One is a simple regression, and then we have multiple regression. Simple and multiple regression. So simple regression, what we do is we test 1x with y at a time. 1x with y. You get a p-value. We always get a p-value. You get r square. What is this r square? We'll learn about that. And we get a linear equation. We'll learn about that. Now, multiple regression, we test multiple x's with y at the same time. We get p-values because we have multiple x's, multiple p-values. We read r square adjusted here. We'll understand what's that, and we get a linear equation. So these are the things we read when we do the test. Now we will be skipping the linear equation in simple because it will get repeated here, and it makes more sense to read the multiple regression equation because it'll technically we'll understand why. Let's start with a simple regression first. In the improve phase folder, you will see this file by the name of regression. Let's understand the data first, and then we will be able to make some sense with the regression test we have. So regression is what we picked up here. Copy paste this data, and Let's understand what does it mean and how do we use this. So this is some hiring firm data, some sort of hiring HR people who are trying to kind of come up with some mathematical model, some statistical model to offer salaries. That's the business problem for them, salaries. They want to offer salary, but what's the right salary we should offer to a different a candidate? X candidate comes in, I offer an X salary, some other recruiter is offering other salary. Uh, there doesn't seem to be a like a set amount or like logical reasoning we got. Well, I offer somebody, I say $10,000, somebody an $8,000, somebody's I offer like $11,000, doesn't seem to have a logical reasoning behind it. Well, it's just the negotiation, probably that's where it helps. We are able to settle down at. Well, unfortunately, we don't want to work that way. We want to have some concrete method of predicting the salary. So, yes, a lot of organizations across the globe have created a lot of calculators using regression. Not for salary only, a lot of for any business metric, you can create a calculator. That's how people have created a lot of calculators, attrition calculator, salary calculator, process metrics, like you can use anything, quality, stuff like that, anything you can create a lot of calculators. It helps you to predict your why, your business output. Let's understand how does it do it? How do we do it? So the basic logic behind regression is to look at your historical data and using historical data, do some analysis and which will help you predict your future data. So if you are talking about predictive stuff, like you're looking at future based on your historical stuff that you worked on. Now, in this case, we wanted to predict salary. So some intelligent people got together and they figured, like somebody said, like, well, I think gender will play a critical role in deciding salary. Well, that doesn't make sense to me, but yeah, I don't want to discourage anyone. Somebody says, well, gender is a root cause that is a significant impact on salary. Uh, Somebody probably feels that females get better salary. Somebody feels that males they get better salary. Well, let's not kind of argue. Let's include it. Well, so we included gender as a possible root cause. Some people said, well, how well do you do in your interview? So during interview there's some psychometric test or some sort of assessment or some sort of exam or some score is done on a scale of 1 to 10. We have some written exam or some verbal stuff, which is basis which we give a score. So some people believe that how well do you do in your interview, that will have a very big role to play in a salary kind of decision. Okay, perfect, we included that criteria also. Well, some people believe that now how experienced you are, that will be a big deciding factor. Okay, well, no fences, we include everything. Now, what we did is we got all the hiring files, historical people like data. These people were hired at one point in time. Ideally, are they working with us? No, it doesn't matter. But yes, were they hired at one point in time? Yes, these people were hired by our organization. Are they currently working or not working? That's irrelevant. But yes, we go back to the historical like data files, hiring files, personal data, and then we check what was the salaries offered to different people. So we found that some female was offered some salary. This is like 88, whatever the salary would be. And when she was hired during the job interview, she scored 4.5 out of 10. And when she was hired, she had 11 years of experience. So we are going to historical data. So we found another file when somebody was hired at 77.3, a male candidate who scored 7.8 during assessment interview, and he had like 6 years of experience, and so on and so forth. So these are all historical data. Now we would like to use this for making future predictions. So we go back to MINITAB. We had started with simple regression first. So 1x with a y at a time. So we go to stat, we go to regression, we go to regression, and it says fit regression model. We click on this. Now that's a powerful tool because it tests everything. Continuous data, the numerical data, it tests your categorical, the text one also. You can test everything with the regression. So continuous numerical stuff, categorical stuff, both X's can be tested here. This is your Y, response is your Y. So my Y is salary, which is Y. Now you have place for numerical X's and categorical. So this is simple regression we're doing. One X at a time. So let's pick up interview score and see how does it relate with your salary. We click OK. We'll take down some values from here and then go back. This is the equation I was talking about, the regression equation, linear equation that we was talking about. I'm going to skip that for a simple one because it is going to get repeated. So we're skipping it. Let's go back to MINITAB. Interview score, p-value. That's an alternate. Less than 0.05 alternate. There is a relationship between interview score and salary. There is evidence here. Yes, there is a statistical evidence which confirms that interview score is related with salary. Perfect. Let's note down the R square. What is R square? We'll understand that. 52.98%. What's it? 52.98. So say interview score, and that's 52.98. That's what we have here. That's my R square. Perfect. Let's go back and test something else. So we got R square, we got p-value, and we got equation. Three things we look for. Let's check this out. Control E, and like we change this interview score to experience. That's mine again, another numerical X. We check this out. Equation I'm still skipping for this one. Experience is again alternate. There is a significant relation. Yes. Perfect. R square 83.26. Experience 83.26. So experience is 83.26%. Perfect. We are done with both the numerical access. We can test the categorical one. So let's delete this. Categorical is gender. Some people felt male, female will decide how much salary do you get. Let's see. Well, equation we're skipping. This is null. Sorry. You had some perception in your mind. Sorry, we cannot help you with that perception. This management is not gender biased. We do not have enough evidence to support your claim. Your claim that male is getting better salary or females are getting better salary. It's just your mindset. Sorry, we do not have any evidence to prove your claim. So practically doesn't matter. Look at R square, 10.06%. Let's make a note of it. Gender, 10.06, that's what it says. Now we know we got alternate for this one, we got alternate for this one, and we got null for this one. Technically, this means there is a relation with this one, there is a relation with this one, and there is no relation. What is this R square telling us? Now R square basically means how much of variability in Y is explained by X. Now that's a fancy technical language. Yes, technically that's what is the technical way. In a layman language, what does it mean? What does it tell us? How much of impact X makes on Y? How big is the relationship? That tells me interview score has a impact of 52.98% on the salary decision. Now, if somebody is offered a salary, the decision of offering someone salary is influenced by interview score. How much? 52.98% of influence is because of the interview score. How well do you do in your interview? That decides this much. Well, great. That's a good piece of information. Experience is even bigger. So that tells me that experience has a very high impact on the salary decision. 83.26% of salary decision is taken because of experience. Gender, if at all, this 10.06% has any role to play, and if it's any kind of impact, but technically null says no relation. If this matters anything, is this a big value of 10.06 or not? We will understand in a moment. But if at all it has any impact, there is impact of 10.06% on the salary decision. But that's what it means. We are getting null, we'll understand this, but is this a big one or not? We will be able to, but whatever it is, it's 10.06 for gender. That's my R square. That's when we move on to the multiple regression to get more clarity about this. Multiple regression, we test multiple X's at the same time. So gender stays here. We put interview score, we put experience, multiple X's at the same time. If you have more X's, then you can do it in batches of 5 each. It's recommended do not exceed more than 5 X's at a time. You can do it in batches. Click OK. Experience, this equation we're still skipping. We'll come to that equation last. That's my last activity. Interview score. Yes, that is a p-value, which is alternate. This is alternate. That's null. Sorry, we do not have an impact of gender. Perfect. We look for R square adjusted, 88.84. Now, what's that? Let's understand first, and then we'll try to build on this. So, R square adjusted, R squared adjusted is 88.84%. That's what it tells us. Now, what is this R square adjusted? Now, we understand that interview score is influencing the decision of salary by 52.98%. Experience is influencing the decision of by 83.26%. And gender, if at all it has any relation or any impact, it is about 10.06%. But salary at the same time, they are influencing all these factors, are putting their effort on the salary decision at the same time. They are not happening in silo. They're not happening in like some other places. Everything is happening at the same time. Your experience is being evaluated. Your interview score is being evaluated. And if you are gender, male or female, that is also, everything is acting at the same time. What is my overall impact as a whole? That's what is R square adjusted, because we already seen the correlation. Some factors positively impact each other, some factors negatively impact each other. So they may be positively impacting or canceling each other's impact. Yes, what's my overall impact? Keeping every force is acting on the salary decision. That's what it says. 88.84 is your overall impact of the model. Quality of the model is 88.84. Now we would like to understand, well, there is how big is every factor. So what we would go is go back to this equation and then let's remove, just to understand this. I want to see how big is this experience. Since 88.84 decision criteria, how much of role is this experience playing? If I remove experience from the model and would like to see what is the drop in the quality of the model. The quality of the model, let's see. I'm saying loss of experience in the model. If I remove experience criteria in the model, what will be the remainder quality? Well, that's bad. 55.74. Your quality of the model has dropped drastically. 55.74. Let's add in 55.74 here. How much did you deteriorate? Your quality of the model has reduced by 33.1%. That's a significant drop. This is a very, very big X, which is playing a very big role in this entire decision criteria. Losing this is going to drop your quality from 88.8 to 55.74. Very big. Can't do that. Well, we wanted to just understand which one is more critical here. Let's bring the experience back and let's see how big is this interview score. Let's remove the interview score and bring your experience. So we want to now understand what is the impact interview score will make in the quality. If we remove loss of interview score, 82.43. So interview score, loss of interview score is 82.43. Is it a drop the way we saw in the previous one? No. 6.41%. Not a very, very big one. Having said that, it's not saying a small one. 6.41 still a very big number, but not as big as experience. This is a big influencing factor. This is definitely big, but not a big one like this one. Like this is absolutely critical. This is what we got to, but these are both alternate and they will have a big impact. Definitely, yes. Let's put them back because they both are alternate. That means there is a significant impact. We already know. Let's remove the gender, which was null, and see what will it do to your quality of the model. Now we got a clean model. Technically, we both have got alternate. 88.78. Loss of gender. 88.78. That's the model loss. That's what it was dealing with. If at all this matters a lot, nothing. Technically nothing. This is nothing. So gender is not a criteria, and that's why we're getting null. It is not playing any role whatsoever in your decision of salary. Whether you male or female, doesn't matter. How well experienced you are, definitely that's a big influencing factor. And how what kind of performance do you do like during your interview? Technically, that is what is impacting. And now we're looking at the clean model. This is your clean model. Quality of the model is 88.78. That's what we would like to maintain. Why? Because we're looking at clean model. Only the alternates, yes. That's your overall predictive model of like what tells you you can predict your salary up to 88.78 by looking at and studying these two values. Let's see Now we coming to the equation. That's what we wanted to kind of understand, the equation part. Let's me copy this and take it to Excel. Let's read and understand how does it help us with the equation part. That's my regression equation. The standard regression equation is written as y is equal to c plus mx. That's what is written. Now, what does it mean? Y means you have salary here. Y is your salary. What is C? C in absolute like a layman language is a constant value, but in a statistical, let me first write down the statistical language. It's called intercept. Intercept. Now, what does it mean? This is a constant, or you can say fixed value of y in absence of x. Now, what still sort of confusing, but let's kind of add. When the value of x is 0, the value of y will be equal to c. We'll validate it. We'll check it out. That's what it says. This is the bare minimum value of y cannot go below c. That's what the constant fixed value. M in a statistical language is the slope. Now in a layman language, this is the multiplier effect of x. X is x. Let's kind of solve this equation that you got. That's what we were looking for in multiple regression. What does it do? Let's put these values. Salary, we want to predict the salary. 53.22, that's my C, which is constant value. Constant is this one. That's C. 53 points. So your salary cannot go below 53.22. This is the base salary that you will offer to every candidate, minimum salary, constant. Then it says plus, we'll leave that plus for now. It says 1.754, okay, 1.754 times experience. 1.754 experience means 1.754 multiplied by the experience. So this is multiplied by the experience. So I'll keep it blank. This is for value of experience. This is whatever I get here. I will multiply that. So 1.754 multiplied by the value of experience will give me this value. Whatever value will come here. Plus, it says 2.105 value of experience. Whatever the value of experience is, I will multiply that with the value of 2.105, and that will give me the impact of experience, the impact of this one. So this is my interview score. Now, if you look at everything, it's getting added up. Look at this, 2.53.22 plus, yes. Whatever is the multiplier of 1.754 is with the experience is this value plus 2.10, whatever the interview score is, this value, yes. All these are getting added up to give you salary. Your calculator is ready. Let's take a simple example and understand how does it help me predict my Y. Let's say there is some person comes in for job interview and this person has zero experience right out of college, absolutely fresher, no experience whatsoever. Okay, no experience, zero. 1.750 multiplied by 0 will be 0. So no impact, no influence of your experience. So x, when the value of x is 0, let's say this is what we're getting, 0. No impact, no experience. Scores 0 out of 10. Entire, like you had 0 score. Well, this multiplied by 0, well, no influence of interview score, 0. What remains is 53.22. When the value of x is 0, y will be equal to c. Y will be equal to c because this plus 0 will remain your y, 53.22. That's your base salary that you any which ways will be offering to every candidate when your x is not available. Well, somebody else comes in, say has 5 years of experience. Well, that was the impact of experience factor. Scores 8 out of 10. Your salary is ready. Somebody comes with 8 years of experience, scores 2 out of 10, offer the salary. Calculator is ready. This is created from your own historical data. Use it, predict your Y, predict your, so you can use this model for predicting your Y by changing the value of x's. You know Y is function of x, Y is impact of x. These are your x's. As your x's change, your Y changes. You know how much Say somebody comes with a 15 years of experience, scores 8.5. Fine, that's fine. That's a salary offer that. Now, keep this in mind. There's a limitation. And what's the limitation? You have to always keep this in mind. Can I come back and give this for 30 years person? Can I offer this? That will be wrong. Why? Did your data contain anything in experience which is equal to 30? Maximum. Do you have any data which is like maximum? What is your maximum thing? Max 21 is the maximum. So this model will predict correct salaries until age of years of 21. So even if for 20 years, this is correct. 21, this is correct. 21.1, this is wrong. This will be wrong. If you want to predict for a higher one, please go ahead, correct your data, create a new equation, because this equation that you created had this maximum of 21. You cannot use this for everything. You cannot have like 40 years person salary. No, that's what it doesn't, because your data created this. If your data was not, it never included this kind of variables like 30 years. Sorry, this data, this equation will not work. So every organization equation is different depending on what their data is, and that is specific to their data. Globally, like when you talk about forecasting, this is how you forecast. You look at your data, your historical data, and that's how you're predicting your Y. Regression is just the linear regression is just the beginning. That's how your entire analytics is further built up. I mean, that's the base of it. But base is this. If you understand this, again, because see, there could be a lot of questions which can come to the mind. Well, why even care about then doing a correlation to sample T and OVA when we have regression? Test everything, job done. Well, yes, you can, but in regression, you don't get details. In two sample T, you are able to say male is better or female is better. Here, you will just get p-value. If you want to compare like three managers, different trainers, different ticket handlers, you were able to see by Tukey which one is bigger, which one is smaller, stuff. Here you just get p-value. So this test of regression is used in improve phase. When you've tested, those were analyze phase test results. When you wanted to find which one is bigger, which one is smaller, which one is good, which one is bad, details will be available when you do the hypothesis test in the analyze phase. This will help you understand which one is bigger. How bigger is this? So this is relevant to the strategy implementation. When you want to implement your strategy, you want to put your efforts in the right places. That's where the regression will come into place. And having said that, can I do regression on Excel? Yes, it does give me a feature. We do have regression on Excel also, but I guess there will be a limitation of the categorical one. But let me try. I haven't honestly tried and tested. I barely use Excel for this, anything. But let's see. I'm sure regression is there. Yeah, we do have regression. I guess we cannot do it for. Let me just try out. Input Y. Let's use the Y. Y we have here. And we can check this out whether it does categorical. It should try. Let's input X's. Let's stay one at a time or three at a time. Let's take all the three. We use three. Are they labels? Yes, we have taken the labels. And that's it. I get. We can click on this OK and see non-numeric data. Excel has limit. As I said, you don't get everything here, but yeah, let's do one thing. Remove this is fine. Let's kind of only use these two. Excel will have problems. So sorry, we haven't got Excel as advanced as, yeah, that's what your test has come. So final testing, whatever we did, we got it here. R square adjusted, we're seeing R square adjusted. This is the R square adjusted, the final test. P values, this is E00616, 10 to the power 16. This is highly, this one, it confirms that there is a relationship. P value, E0, the moment you see E, that means bottom line you got into less than 0.05. So, and the equation can be created from this one. Say if you say 53.22 plus 2.105, yeah, this equation, this is going to come from here. If you look at the equation, that was the equation we were getting in our MINITAB test results also. Look at this, everything you're getting from here. Copy, paste, have a look at it. Is it not giving you this value? Yes. Is it not giving you 1.754 of this one experience? Yes. 2.105 interview score. You're getting the equation, you're getting the R square adjusted, you are getting the p-value, which is also here. You want to do it with one single X simple regression, you do simple regression. Y is there, X only with one variable, do a simple regression. You can still work with it, just one factor. You look at R square here, 52.9. Having said that, one more thing, just want to make sure that we all remember this and understand this. When we did correlation, is correlation related with regression? Absolutely yes. Advanced version. Correlation comes with R, this is R square. Same R, you double it up, you get R square. So same data, if you test it on MINITAB, say let's quickly test this out. Stats, basic statistics, you do a correlation test. Say salary versus say you do experience, your correlation value R, and that's the other one is R square. Look at this R, 0.912, 0.912. Do R square, this 83.17. Let's look at this 83 point whatever this one. It's coming here. Same R square, double it up. That's how you get. I hope we're good with this. Everyone understands the equation, the regression part of it. Is it okay with everyone, or is it too much?
Can you just tell me about M? You said it's multiplier effect of X.
Yes, this is the M is the one. These are those 1.754, 2.105. That's what is
Okay,
getting
this is
multiplying the X here, multiplying the X value.
Okay.
This is M1, this is M2, and this is X1, X2. So multiple X1.
All right. Yeah.
Okay. Okay, one quick thing. So from tomorrow onwards, so we have 3 more sessions which are lined up. So tomorrow, then on Friday, and then on Monday. That's where we'll end. So we have 3 more sessions, and these will be until 9:30 in stand time. So technically, it's like 30 minutes more in every session. So we'll have a 3 hours long session. We'll have a break in between. So we'll try to ensure that there's it's not too much given the time. That's why we're trying to kind of add up the break here. So, but yes, 3 more sessions which are there, and we'll have 3 hours long. So we have been going for 2.5 hours. We'll have extra 30 minutes on all these dates. So we'll just cover up. We'll yet to cover up the improve, control, and the portion of lean that we will kind of go through. So I hope this is the schedule is fine with everyone. The starting time is still the same. We'll be ending 30 minutes late. That's, I think you all should have received this communication from IMC.
Yeah.
Yes.
Perfect. All right. So, all right. So I'll share this data with the Excel sheet again back with the, in case, like, just give me one quick moment. Let me share it here with everyone in case if somebody doesn't get it, well, I'm sure like they will be sharing it, but yes, like, give me one quick second. Let me just share this quickly. This is the file that we're working. Click on it and it'll get downloaded on your system. So that's how we do it. Yeah, please get it downloaded, and in which case I will be emailing it to the IMC team, and they will in turn share it with every one of you. Is there any questions? You may let me know, or else we can call it today. Any questions? Okay, I guess no. All right. So please do take good care of yourself. Let's catch up tomorrow, same time. And till then, please, again, that's what, like, good night for people who are going for sleep and people who are in the morning time zone. Hope you have a good day. Thank you. Thanks.
Thank you.
Thank you, everyone.